Hello, my name is Seung-hyuk Baek from the Republic of Korea, and I'll present segmenting unseen industrial components in a heavy clutter using RGB diffusion and synthetic data. The authors are Seung-hyuk Baek, Jong-won Kim, Leon Gang, Seung-jun Choi, and Gyubin Lee from Gwangju Institute of Science and Technology, GIST. Instance segmentation of unseen industrial components is necessary for autonomous industrial systems such as industrial bin picking. From the RGB and depth image pair, deep learning models such as Mask-R CNN can be trained for pixel-wise instance segmentation. However, building a large-scale high-quality dataset is crucial for robust and industry-applicable performance, and repeating the data collecting and labeling procedure manually is costly and often infeasible. Moreover, industrial components are textureless, reflective, and often found in a cluttered and unstructured environment with heavy occlusion, which make it more challenging to deal with unseen objects. To segment unseen industrial components under fast production, we train the category-agnostic instance segmentation model using only synthetic data. Then, we transfer the model to the real world without fine-tuning using real-world data. In summary, we present a synthetic data generation method that simulates an industrial bin environment by randomizing textures and adding depth noise. Also, we propose an RGB diffusion Mask-R CNN with a confidence map estimator, which exploits reliable depth information in multiple feature levels. We demonstrate that our method, which uses only synthetic data, could be an effective solution for unseen industrial components segmentation. Recently, the concept of unseen object instance segmentation, or called as category-agnostic instance segmentation, has been proposed. Daniel Chuck proposed a synthetic depth Mask-R CNN to segment unknown objects in bin-picking environment from synthetic data. Xie has been proposed the method to separately leverage synthetic RGB and depth for unseen object instance segmentation. Though the results are promising, the unseen object instance segmentation for industrial applications has not been studied in detail. Segmenting unseen industrial components is quite challenging due to its unique property as they are textureless, metallic, and shiny. However, there are only a few industry-relevant public datasets, and these datasets lack variation in the number of images and objects. For example, TRES dataset only includes textureless objects, while ITODD only offers 800 scenes of industrial objects. For metallic component detection, Ri et al. Proposed a method to generate photorealistic synthetic training dataset for the segmentation of wrenches in the real world. However, they do not concern detecting novel objects, but focus on the segmentation of only a single wrench, and fine-tuning using real data should be performed. For the detection of unseen industrial objects, we generated a synthetic large-scale dataset. We collected a total of 149 3D CAD models from public datasets, including industrial objects and household objects. Then we configured a virtual bin picking environment using VREP and captured RGB depth segmentation mask pairs. As a result, we obtained 30,000 training image pairs and 5,000 validation image pairs. For RGB images, we adopted domain randomization by randomly texturing the objects. By doing this, we can encourage the model to learn domain-relevant features such as the shape and edges, while reducing computational costs and human efforts required to optimize simulation environments. For each iteration, we vary the position, texture, and color of each object. Additionally, the light intensity, camera distance, and orientation from the center of the beam were adjusted. We also generated corresponding instance mask and synthetic depth. While initial synthetic depths are complete and precise, depth maps in the real world are noisy and have missing values. We add realistic noises and sparsity to the synthetic depth map using 3D paralleling noise, sparse edge noise, and search and paper noise. Exploiting a depth map with an RGB can improve the segmentation performance since depth maps are likely to change sharply on the edge of objects. Thus, we propose a RGB-D fusion mask called CNN with a confidence map estimator, which views only reliable depth information along with RGB in multiple feature levels. From the RGB and raw depth map input, RGB-D fusion mask called CNN are trained to predict category-agnostic instance mask. To handle different modalities with a separate network, we divide the feature extractor into RGB and depth branch for each modality. As a RGB-D fusion strategy, we adopted a fusion module and confidence map estimator to the mask CNN. From the raw depth map and validity mask, the confidence map estimator assigns confidence map with 5 convolutional layers. The confidence map records the pixel-wise reliability and it is multiplied with depth features to apply spatial attention on depth map. Through this operation, features with high confidence become larger values, while the features with lower confidence become smaller. Then, RGB and depth feature maps are concatenated and converted into fused feature map. Finally, the fused feature maps are fed into the feature pyramid network FPN. This confidence map estimator and fusion module applied in 4 different scales. Thus, our model can effectively utilize the both RGB and depth in multiple feature levels. We evaluated the performance of our model on unseen real-world objects. We captured RGB-D images in a beam environment using a commodity-level RGB-D sensor, and we labeled them manually. As a total, the real dataset includes 60 low occlusion images and 40 high occlusion images. We compared the performance of our model with mask CNN baselines with different input modalities and RGB-D fusion. Mask CNN baselines with RGB inputs show reasonable generality over unseen objects. This shows that our synthetic data generation methods can be applied to unseen industrial object segmentation without fine-tuning using real data. Among the baselines, our methods with a confidence map estimator achieved the best performance compared to all others. This suggests that our model can learn to extract only reliable features from a raw depth map with a confidence map estimator. These are the inference results of baselines and our model. And these are the one-to-one comparisons between RGB-only models and proposed model. Our model can capture unseen objects very sharply and clearly. Here's some demo on real-world scenario using our proposed RGB-D fusion mask CNN with a confidence map estimator. Note that our model trained using only synthetic dataset and no temporal information is used. Thank you for your attention.